All right, so here we go, Boolean algebra. Okay, so essentially, at its core, Boolean algebra is a way to take our min terms, okay, whether they're terms that we've been given or we've derived from a circuit, and it's going to allow us to simplify the logic behind those circuits using algebraic rules, okay, and properties, okay. So just like you might simplify something in math, right, by reducing variables and things like that, we're doing a similar thing here, okay? Except that our variables here are connected to our gates, and ultimately that's going to mean reducing the number of gates for our circuit, but maintaining the function of the logic. So, for example, looking at these two different logics on the left and the right here, they are actually the same logic at their core. Okay, so the circuit would function the same way, and these three terms on the left would still actually work and produce ones on or a light on the final output of the one on the right. Okay, the difference is that we can achieve the same logic with a whole lot less gates, which, as we've said, translates into a more efficient design for design, for building, construction, production, and all those good things. Okay, so it's a savings all around. Okay. So this whole concept of Boolean algebra, invented by this guy, George. Okay. Always crazy to me. He's thinking about this Boolean logic type of stuff. Computers were a distant, thought in someone's mind. In fact, back when this guy was alive, I'm sure electricity was still magic. So it's always interesting that they've thought these types of theorems well before there was an application for them. So, okay. All right. So let's take a look at this. Essentially, there's a bunch of theorems that we have that we're going to operate on. I have attached that page, and I think I printed out copies. You guys that are here, make sure you get a paper copy for me before you leave today, okay? And let me just open up the sheet so you can all see it here. And you may even want to have that sheet open in another tab while I'm going through. Okay, so basically we have most of our Boolean theorems, 1 through 9 over here, are the core theorems that you're going to be using to make reductions. You can see on most of them, right, we've got two terms on the left and it reduces to a single term on the right, okay? In most cases here, it's going to reduce to a 0, an x, or a 1, right? A 0 means it's always off, a 1 always on, and an x is the actual variable or the switch that we have there, okay? We have some other laws as well, okay? Commutative laws, associative laws, and distributive laws. These are just your basic algebraic laws. You already know these, believe it or not. It really just says, for example, it doesn't matter the order in which we add or multiply so long as everything gets multiplied and added, right? Okay, so you can rearrange it as needed. Same thing here in the associative law, okay? We can kind of group and move things as we need to so long as we don't break, our please excuse my dear Aunt Sally rules, okay, or order of operations, and that's fine there. You're also able to both distribute, okay, like they've done the top one, or FOIL things out, or go backwards if need be to isolate certain variables to perform then a Boolean reduction. Okay. So this will make a little more sense as we go through, but I just want to let you know that that's the sheet you're going to want to have with you at all times when you're doing this type of stuff, because you're going to need to refer to the rules and see which ones apply. Okay. All right. What they've done here is they basically laid those 9 theorems out against the gates that they kind of represent. And if we think about it in terms of switches or inputs here, the laws kind of make sense. Okay. So with the first law here, we have X, which would be an input switch, times or ANDed together with a 0. Okay, let's think about this for a second. We know that an AND gate needs 2 1s on the input side to produce a 1 on the output side, correct? Okay, so with that in mind, if one of the inputs is always a 0, okay, it does not matter what the other input is because the gate will never work, right? Okay, so with that in mind, this situation can never happen. We can't have 2 1s because they've said that 1 isn't always a 0, and same thing here. It doesn't matter if or y cannot be a 1 because it's telling us here that it's always a 0. Okay, so the only possible output for that is a 0. Basically, that gate would reduce down to nothing. Okay. Here's a similar one, all right, except it's kind of the opposite, right? If one of the inputs is always a 1, then we're really reliant on whatever x is. So if x is on, then the gate will pass, right? So if x is off, then the gate will not pass. But it really just depends on that other input, right? Because we're guaranteed a 1 on this side, okay? So the double 0 will never happen because it's always a 1. All right, and similar thing here, y will never be a 0 because we've been told it's always going to be a 1, okay? All right, similar over here for number 3, okay? If both inputs happen to be the same, and again, you might be asking yourself, well, why would you wire 2 into the same AND gate? The answer is that you wouldn't, except that through other reductions, you might end up with the scenario. So from a previous algebraic step, you might end up with x times x, and it would reduce down to a single 1, right? Okay, 1 times 1 is 1, okay? Theorem 4 here, okay, again, this one makes sense. It can only ever be a 0 because we can't, if 1 is x and 1 is not x, it's the same input, so they can't be both things at the same time, right? It's got to be one or the other, and again, therefore, that gate would never pass, okay? All right, here's basically the same set, except it's all with the OR gates, okay? These are a little more free, though, right? So if we have a 0 going into one side, remember the function of an OR gate, we need one or the other or both. And so it doesn't really, it's really dependent upon the x. If 1 is a 0, if x is a 1, it goes by. If x is not, then it doesn't, okay? So basically, the output is dependent upon the single input, okay? In theorem 6, this is actually the kind of the opposite. If we're guaranteed a 1 on one side, it does not matter what x is, the gate will always pass, right? Okay. So if x is on or off, it makes no difference. The 1 on the input guarantees us a 1 on the output. Okay. Number 7, similar again to one of the AND gates, right? If they're both x, it really just depends on if x is a 0, it's a 0 on the output. If x is a 1, it's a 1 on the output. Okay. And then here, again, similar to the other one, except we're guaranteed a 1 at the end. It can't be both, so that means one of them must be on. The other will be off, but if they switch, then the other one is on. Okay, so we're guaranteed a 1 on the output there as well. All right. And then theorem number 9 just says, hey, if we actually, if we invert something and then invert it again, okay, so x not, we actually just ended up with x again, right? Okay, if you flip a coin and then flip it back, you're back at heads, right? All right. We haven't really gotten into these double knots, but we will, although I don't think they show up in our beginning math here, okay? All right. So let's take a look at a very basic example here. I'm going to guide us through it, and then there are a few more in the PowerPoint, so I may ask you to do some on your own. You may want to have a scrap of paper next to you so you can attempt to do some of these. And, the answers are in the next slide, but I'm going to highly encourage you to do it on your own and see if you're actually getting the concept, okay? So right off the bat, if we're looking at this one here, okay, I can already see some very obvious redundancy, and hopefully you're seeing it too, where there's some pairs that are going to match right up. For example, we've got A and A here, okay? Looks like if we have 2 of the same thing, why do we have that? We probably should just have 1, okay? And then here's a scenario where we have C and then not C grouped together. Again, they're going to have somehow cancel out. So let's go ahead and take a look at our formula sheet, okay? And we're going to discover which ones are the ones we need. So here's the one for the second pair there. So I've got x times not x is going to equal a 0. So let's go ahead and do that one first. So here's C and not C. Keep in mind, too, that the sheet, even though it's displaying x's, you're basically substituting that with any letter that you're faced with, whatever variable they decide to use for that particular activity or problem, okay? And in fact, you can even group, if you have 2 letters that are grouped together against 2 similar groups, if that makes sense, right? That can also be represented by the same x. So, for example, if I had AB and AB, I can pop in that group of AB for a single x in the formula here, okay? So AB times AB would reduce to a single AB, if that makes sense. Okay, you may come across that. So Let's go ahead, though, back here. So C, not C, would reduce to 0, and the D would come down. Okay. It's not a bad idea to get in the habit of writing the rule down just at the beginning here. I know they ask you to mark out your steps, so that was rule 4. In the activity sheet, they do ask you to kind of write those out. And it helps me just to make sure that if you do make an error, we can correct why you made the error. Okay. So let's go and check out now AA. All right, that is going to be rule number 3 here. So x times x equals x, or in our case here, all right, rule number 3 is a times a is going to reduce to a single a. Okay, the b comes down. So does the plus. Okay, I don't see any real obvious reduction from here because I don't really have any other similar terms or ones or zeros. 0 over here, though, and D is going to reduce again. So let's go back to our sheet and find that one. So here we go. X times 0 is 0. Okay, again, the order doesn't matter because we're multiplying. So as long as we're still multiplying, we're good. This is going to reduce to a 0. Okay, and then AB. Again, I'm treating AB as a group now. This is really basically an X. So AB plus 0. Again, one more step here is going to be rule number 5. Okay, x plus 0 equals x. Or in my case here, AB plus 0 is going to equal just AB. Okay, I think that was number 5, right? Sorry, I'm writing with the mouse here. I apologize. It's a little sloppy. I forget this was rule 3 as well. No. Anybody catch that rule? I missed it. All right, number 1. Okay. How do we feel with that so far? Thumbs or eh? Okay, I'm seeing some thumbs. Okay, good. All right. So let's move on and take a look at another one. Okay. Okay, here they've done it out and they got all the numbers and everything as well. So we came to the same answer, which is great. Okay, this one's a little longer. So here's what I want you to do on your piece of paper. Okay, I just want you to circle in that top line there what terms you basically think are going to do a little bit of reduction. Okay. So, get your piece of paper, write it out. Okay. And then I want you guys just to, again, do some basic circles around the groups that look like, hey, I think that's probably going to reduce. Okay. And then we'll actually map it out. If you guys want, there's some paper right here if you want to follow along. All right, so here's the basic groups that I see quickly. I see this BB looks like a reduction. I see not C looks like a reduction. All right, I see B1 and not B0 all look like some reductions. Okay. So let's take a look at some of the rules here. Okay, these ones that are identical to each other, so B, and not C, are going to be ones that reduce right down to themselves. So that's going to be law 3 here. And even though it's not C and not C, really what you're looking at are two equivalent terms. So even though it doesn't show not X here, again, it's just showing that you have two terms that are similar. The letters are kind of interchangeable there. Okay, so BB is going to reduce to just a single B. The not C is going to come down. Okay, similar fashion here. Not C is going to reduce to a single not C. All right, and then we have this one, okay, B into 1 and not B into 0. And let's go take a look. So rule number 2, X and the 1 is X. Okay, and then X into 0 is 0. Okay, so they're both, in those both cases, the one with the 0 is reducing to a 0. The one with the 1 is reducing to a 1. So this is going to come down to a 1, and the not A is going to come with it. And the not B 0 is going to reduce to a 0, and that A is also going to come with it. Okay. All right, does anybody see any other clear reductions here in the step 2s? Folks in class here, does anyone, you can shout it out if you see do you see some other similar groups? Okay, so we've got a B not C and a B not C. Okay, so those are going to reduce down. So let's take a look. Okay, so X or X equals X. Okay, so this group of B not C and this group of B not C are going to reduce to a single B not C. Okay, very good. And then in a similar way here, right, we had a 1 that reduced the B and a 0 that reduced that B. We've got the same 1 and the same 0 hanging around, except now they're on the A's, right? So it's almost the same rule. It's just now trickling over to the next one. So not A and a 1 is going to reduce again to a 1. I take that back, actually. That doesn't seem like it's going to reduce to a not A. Oh, did I make that mistake? Nope. X times 1 is X. So, oh, I see what you're saying. Did I put the 1 in? Yeah. You're right. My mistake. That's why that wasn't making sense to me. Okay. Yes, thanks for catching that. Okay, so that should have reduced to a B, not a 1. My bad. Okay, so in this case, this will not reduce then, so we're going to get rid of those 2 lines. But the A times 0 will reduce, okay, to another 0. Okay, and then we've got this A not B is going to come on down. We are going to have this A not B plus 0, and that will reduce. Okay, back to our rules here. And here it is here, 6, x plus 1 equals 1. Or no, sorry, x plus 0 equals x. And so A not B plus 0 is going to reduce to not A B. Okay, and then we have our B not C from the other side. And at this point, it looks like we don't have any more similar terms, okay? You could potentially extract a B from both sides. You know, an alternative here would be is that we can factor out a B, and we could be left with not C or not A times B. Okay. So you know that is possible. You know, this would require one inverter and a 2-input AND gate, an inverter and a 2-input AND gate, and an OR. This would require the inverters, 1 OR gate, and 1 AND gate. So actually, this might be more simplified. Okay. So I would say if you got to this point, I would be very happy with your skills. But if we're totally thinking about gate efficiency, this may end up actually being more simplified, right? We actually can drop a gate off just by extracting that at the end. Okay. How are we feeling after that one? A little more comfortable? Or more confused? Okay. And you can say they brought it down. They did stop here, which again, I think is perfectly fine. They're trying to leave it in the sum of products form, right? You know, here we're kind of shifting to product to sums form maybe. But again, it kind of very similar in the end. Okay, still a big reduction from the beginning here, right? Okay, look at what we whittled it down to. All right, here's just examples of the commutative law and the associative law, okay, and the distributive law. Again, these are all of your more of your core algebraic stuff. You've been doing these things, you know, for years now, whether you knew it or not. Okay. Right. So let's take a look at this one. All right. Right off the bat, we can see there's some similar letters, but there's no real groups here that are in fact, directly similar that we can reduce. So even though it's going to look bigger for a minute, we are going to want to FOIL this out, okay? So we're going to end up with R naught R. Okay, we should already be seeing a little reduction in our eyes there. Let's see, we've got R and T. And then we've got not S, not R. And which one am I missing here? Not S and T. All right, and let's not forget our not R, not T from the beginning. All right, so again, does anyone see any real obvious ones right off the bat here? Yeah, R not R to me is a real obvious one. Okay, we've seen that already a few times, so let's see if we can reduce that. So, okay, R and not R would be like X and not X. That's going to reduce to a 0. Okay, and then really anything that gets grouped in with that 0 as far as an OR is going to reduce down to just that other term, right? So if we kind of block these two off temporarily here, okay, that is going to be like X plus 0 equals X. And so that 0 is just going to disappear. So we're left with not RT. Okay, and I'm seeing a similar pair if we bring regular RT down. Okay, here's an example where we're going to want to, again, pull out the letter T. Okay, so by extracting T, so we divide away T, right? We're left with not R or R. And we're actually end up with a very similar thing on the other side here. If we extract, well, we could extract, there's a similar not S, but I guess it's not going to really reduce overall. So let's do this one first, right? So not R and R. It was an OR, right? Is going to be like X plus not X, which is 1. Okay, so that we're running out of space here. It's going to reduce to a 1. Oh, I'm out of slide space. Okay, and then basically T times 1 is going to be T. Okay. Sorry for the side noise there. Okay, so T times 1 would have ended up being just T. Okay. I'm going to rewrite it over here. Sorry for all the arrows here. So we've got plain old T. And I'm actually going to reorganize this. I'm going to bring this not S T here. Okay, and that not S, not R, I'm going to leave off to the side here. Okay, so believe it or not, we have another reduction that we can do here. There are some other laws. Okay, we can also do a little algebraic trickery here. So they have you do this often, and when I was first learning this was not something that was very clear to me. But we're going to put in a 1 here, right? Think about just any number in math, right? Any number times 1 is itself. Does the 1 have any real impact if you multiply it by 1? Doesn't change the number, right? So mathematically, we haven't done anything wrong by saying, hey, multiply by 1, right? The number's still the same. Here's the trickery I'm going to do, though, okay? Now we're going to factor out T. You nailed it, Jimmy, okay? So T comes out, and we're left with 1 plus not S, okay? Now we've got some isolation, and there's definitely a law here that we're going to be able to reduce with. Okay, so X plus 1 equals 1, even though it was a not S. Again, it doesn't matter. So we're left with a 1 there. Okay, and again, we're going to have T times 1 is itself. Okay, eventually. Put my little multiplication group in there. Okay, and then we had SR still over here. T times 1, again, going to reduce down to just plain old T. And then we're going to bring that in for the final answer. So T or not S, not R. was my final. Okay, let's see how we did with their results here. Okay, so similar thing. All right, they FOILed it out. We reduced the 0 here. No, they did something a little bit different there, but we came to the same conclusion in the end. Okay, they did. They factored out the t. Oh, they factored the t out all three of them at once. That was a good idea. Okay, so I think this is a good lesson here, though. They did it slightly different than I did. We came to the same result, and it's possible to come to a different endpoint and still kind of get a good answer, right? Okay, there's varying levels of reduction, and depending upon where and how you reduce in a bigger formula like this, you could end up with a different looking answer than someone else, and they both could be a reduction. One may end up being better than another for one reason or another. And again, this is something a good engineer would probably do, is kind of play out multiple scenarios to see which one's really the most efficient, right? Okay. Doing a little extra math doesn't cost anything, but making $1 million manufacturing mistake does. Okay. All right. I think they have one more for us here. How are we doing? Do we feel okay? Have we hit our limit? Do you want me to go through this one? No reply? Have we zoned out? All right. So I'm gonna stop on this one then. I'll come back. Maybe we'll take a look at this one next week, just as a refresher. So I'm gonna stop my recording at this point.